All right, let's dive in. Today, we're going to talk about an algorithm that looks simple but is an absolute superpower in computer science: binary search. This is the magic behind how huge systems can find exactly what they need in, like, the blink of an eye. So let's get into it. Okay, so picture this. You've got a list, a really, really big one. It's perfectly sorted and it has 1 billion items in it. 1 billion. That's a number that's kind of hard to even wrap your head around.
Now, here's the big question. Somewhere inside that massive sea of data is the one thing you're looking for. How fast do you think you could pinpoint it? Seriously, what would your strategy be?
Well, if you did the obvious thing and just checked every single item one by one, that's called a linear search, you could be there a while. In the worst case, it could take you a billion checks. But what about with binary search? You're looking at about 30 checks. No, not 30 million, just 30. That mind-blowing jump in efficiency is exactly what we're going to break down.
So let's really focus on this billion item challenge. This is the kind of massive scale problem that binary search was born to solve. See, the key isn't to work harder, it's to work smarter by throwing out gigantic chunks of the problem with every single step.
So how in the world does it do that? Well, the core idea, the secret sauce, is actually incredibly simple. It's all about the art of having. Instead of sifting through every piece of data, you just find a clever way to throw away half of it, over and over and over again.
You know, the best way to think about it is like a bookshelf. Imagine all the books are sorted perfectly by title. You're looking for a specific book. You wouldn't start at the A's, right? No way. You'd jump right into the middle. You check that book's title. Is your target book before it or after it alphabetically? If it's after, you now know with 100% certainty that your book is somewhere in the right half of the shelf, so you can completely ignore the entire left half. Boom, problem cut in half. And then you just do the exact same thing again with the books that are left.
And that right there is the formal definition. The key word, and this is the absolute non-negotiable rule, is sorted. If the data isn't sorted, the whole having trick falls apart. But when it is, you can just keep dividing your search space until you zero in on the answer with lightning speed. So the bookshelf analogy is great, but how do we actually tell a computer to do this? To really implement it, we need 3 key things: pointers to mark our search space, a midpoint to make our guess, and a set of moves to shrink that space down.
Okay, first things first, we have to define our search space. We do this with 2 pointers, which we usually call low and high. We stick low at the very beginning of the array and high at the very end. The answer we're looking for is somewhere between them. Step 1 is easy. We just find the element that's sitting smack in the middle of our low and high pointers. This mid element is our pivot point. It's where we're going to make our big decision. Now for the magic. We compare the value at our mid position to the target value we're looking for. Let's say our target is bigger than the middle value. Well, because the whole array is sorted, we now know for a fact that our target can't possibly be anywhere in the left half. So we just throw that whole half away by moving our low pointer right past the middle. And then we just do it again. Our search space is now half the size it was, but the logic is exactly the same. Find the new middle, compare, and discard the half where the target can't be. Just look at how fast those low and high pointers start closing in on each other. That's the real engine of binary search right there. Now, here's the thing. The idea is super elegant, but getting the implementation perfect is notoriously difficult. There are a few classic traps that have snagged even the best programmers out there. Forgetting the array has to be sorted is, of course, a showstopper. But the really subtle bugs are in the details. Messing up your boundary updates by just one, which can accidentally throw out the right answer, or even worse, creating an infinite loop. And then there's the most famous pitfall of all, the integer overflow bug. So this little line of code has a pretty amazing backstory. For decades, a lot of people, and I mean a lot of standard libraries, calculated the middle like this: low plus high divided by 2. The problem: if low and high are huge numbers, adding them together can actually exceed the maximum value an integer can hold. It overflows and you get a garbage answer. This exact bug was hiding in plain sight in major software for years. The formula you see here is the fix. It's a safer way to do the same math, and it's the version you should always use. So once you get the basic search down, you unlock this whole new level of problem solving. See, binary search isn't just about finding if something exists. It's about finding specific positions and solving problems that, on the surface, don't even look like search problems.
So what happens if your sorted array has duplicate numbers? The basic version will find any one of them. But what if you need the very first one, or the very last one? This is where the logic gets really subtle. Let's take the leftmost match. Even if you find the targeted mid, you can't just stop. Why? Because there might be another one even further to the left. So what you do is you make a note of this potential answer, and then you tell the search to keep looking, but only in the left half. That's why the boundary move is high equals mid. You shrink the search space, but you keep mid in play, just in case it's the one you're looking for.
And this is where things get really cool. We can use binary search on the answer itself. Take this classic problem. We're not searching through an array of items here. We're searching through a range of all possible answers, all possible shipping capacities. And we can do that because there's a hidden sorted property. If a ship with capacity X works, then any ship with a capacity greater than X will also work. This creates a dividing line between no answers and yes answers, and that's exactly the kind of pattern binary search is built to exploit. Okay, let's bring it all home. When you put all this together, you can see why binary search is a genuine superpower. It all comes down to its unbelievable, almost ridiculous efficiency. In computer science, we call this logarithmic time complexity, or O log n. Now that sounds fancy, but all it really means is that the time it takes to find something grows incredibly slowly as your list gets bigger. If you double the size of your list from 1 billion to 2 billion items, you don't double the work. You just add one single extra step. That's it. I mean, this picture says it all, doesn't it? As your data grows, the work for a linear one-by-one search just skyrockets. But the work for binary search barely even moves. The gap between them isn't just an improvement, it's the difference between something being possible and being completely impossible. All right, so if you remember anything from all this, let it be these things. First, it absolutely requires your data to be sorted. Its power comes from cutting the problem in half every single time, which gives it that amazing O log n speed. Make sure you get comfortable with the three main flavors: standard, leftmost, and rightmost. And please, please, always watch out for those tricky off-by-one errors and that infamous overflow bug. And that really brings us to the final thought. Binary search is so much more than just a piece of code. It's a way of thinking. It's about learning to spot the hidden order in a problem so you can tear it apart. So the question I want to leave you with is this: what other huge, messy problems out there, maybe even problems that have nothing to do with programming, could be solved if we could just figure out a way to cut them in half?